This was a very last-minute presentation, and I admit that and my design was more to just kind of raise a few issues rather than give a more formal presentation. I'm gonna give two examples, one in sort of recognizing patterns and one in terms of anomaly detection. Oops. First of all, I'd like to just mention briefly about a very recent project associated with generating model zones for a large-scale employment, land use, transportation, economic model that's being applied to Los Angeles. It's called ReluTrans, and it was developed by Alex Annis at University of Buffalo. And it's part of a multi-campus project research initiative at UC. And the next one is going to be in terms of measuring spatial efficiency of emergency services. These are more large-scale kinds of issues rather than looking at the micro-scale behavior. Okay, so the example one is the problem of aggregation. It's an aggregation problem where we're going to cluster 4,109 TASs into 100 planning areas or units. This could be considered maybe like a classic zonation problem of Stan Openshaw. And you can also think of it as almost like a political districting kind of problem, except that there are special notions associated with it in order to be at the underlining fabric for modeling for this ReluTrans model. So the planning regions needed to be contiguous. They should not be too large. They should be compact. The traffic within the region, and this is where it's sort of like a political districting problem, but we've conditioned it with a transportation-minded constraint. The traffic within the region should be less than X% of the total commuting traffic generated by the region. Otherwise, that if each region is too large, then you are missing quite a bit of the traffic because it's just within the region itself. So, and then known subcenters, these were business subcenters and so forth, should be part of only one region, and actually they were seeds for individual regions, although for the 100 regions that we were generating, we had approximately 50 subcenters that were already defined. And then regions should not cross a physiographic boundary like the San Jacinto Mountains or something. Doesn't make much sense. So this is a map of the entire area that let me see if I got this right. In terms of interior, Los Angeles, Orange, Riverside, San Bernardino, and Imperial counties. And when you're talking about aggregating 4,109 TASs into 100 regions, you're talking about a really quite large clustering problem. And it's a rather daunting one when you first think about it because in terms of the classic literature for political districting and zonation and so forth, most problems are not this large at all. So we have, there's ways that we can formulate it as an integer programming problem, but the most recent paper that does this, which appeared in Geographical Analysis a few years ago, the models that are designed to solve these kinds of problems can really solve and optimize at most 50 units, clustering into less than 50 areas. And one of the biggest issues in formulating these kinds of problems is the continuity constraint, that you need to have each of these areas contiguous. Okay, so there's one other element that we added to it, and that is that we added, rather than using an isoparametric quotient as a measure of compactness, we actually measured compactness based upon lost my train of thought. It's moment of inertia. And the moment of inertia is more of a physical term in terms of this, basically the square of the distances to summing from every pixel, if you will, of a region to the center, which is the geographic center of mass. And when you start to look at this kind of problem, it is highly nonlinear. So we're really talking about an objective function where we add the component of minimizing compactness, or I should say maximizing compactness is a measure here that gives us from 0 to 1. It means that we are now solving a highly nonlinear integer programming problem for which if it was just a linear integer programming problem, we could do at most 50, cluster at least 50 units into something, not 4,000 plus into 100. So we had to look at devising a heuristic. Now, we pulled out all of the regular kinds of things that you can imagine in terms of simulated annealing, taboo search, grasp, greedy, and so forth. I just want to point out that since we were aggregating 4,000 TASs into 100 zones, and each of these 100 zones has a compactness measure of 0 to 1, that they would perfect compactness of all 100 zones would add up to 100. And we're looking at the objective function here, and you can see here that the objective function here says 89.9 for at least a couple solutions that we generated, which says that most, nearly all of these were relatively compact zones, okay? Now, these are relatively compact zones, all meeting this X% of traffic, no more than X% of traffic generated within the zone as compared to between zones. So what does this map look like? And this is the whole reason why I was telling you this long story, is that there are a number of areas here that are nice compact zones. But there are anomalies. Look at this one. Here is a zone centered around a zone. This is what the optimization model was able to generate. We're talking about donut holes, so to speak. This is what Costas refers to, my donut hole map. Now, the issue is this. If this is the kind of map that makes a lot of sense for transportation, one of the things that is really quite an anomaly here is why donut holes? Why not a map of compact zones that look like this? That's a question I leave to you, but it also gives another element of interest here, is that if we go back to lots of other kinds of applications like political districting, maybe the most compact and meaningful zones for political districting really actually are these donut hole kinds of maps. But let me go back. Let me go on to example number 2, because I don't want to take a lot of time. I think the one of the ideas of this particular workshop is to sort of spur discussion and where we might go with various research topics. Okay, so this second example is looking at public services like fire protection and how efficient and adequately are they. And there's lots of ways that we be able to model them in terms of whether coverage is well covered in terms of average response time, percentage of calls served within a standard, dollars per person for the service per year, and even perhaps anomalies in service and patterns in service. And I think you'll see a little bit of what I'm getting at here. I'm more of a serviceman rather than looking at the individual micro behavior of traffic and travel demand. So let's focus on fire protection services. Obviously, fire protection services don't happen without transportation. If we will, LA County uses a number of political entities that provide fire. And so there's the City of LA, the County of LA, and many, many municipalities, including even the federal government. The City of LA Fire Department operates at 114 locations. Their budget is in excess of $750 million a year. The County of LA Fire Department operates 171 fire stations and serves unincorporated areas as well as 58 municipalities. And they have a budget of $979 million a year. Then there are at least 100 other stations operated by municipalities like Culver City, Santa Monica, City of Pasadena, and so forth. And if you add up all this money, you'll find out that just the yearly cost of providing fire services in Los Angeles County, and this is just the fire department across the county, is more than $2 billion a year, and it's really more than what the state gives to University of California for its operations. Okay. Now, where does this all lead? Well, what it amounts to is that we asked this chief information officer for the County of LA to give a list of all of the fire stations in the county, which we received. We also developed, which I don't have time to here to describe much, we also developed a cyber search tool to actually look for fire stations. And this is comparing the results of those two, the county's list, the government database, and the cyber search. What it amounts to is that the government database had 62 stations that were not in the cyber search database, and the cyber search database had 56 stations that were not in the government database. Now, we compared entries, and we found out that there were slight address issues. There are 32, so 62 stations not in the cyber search. There were 32 that were actually in the cyber search based upon addresses, so that left a remaining number of entries of 30. And the same thing here, 56 minus 32 is 24. So we have to resolve these two differences of 30 and 24. Upon reconcilement, we found out that 17 of these 30 stations were obsolete and had been closed. We also found that 24 of these stations were current stations. So that what it amounts to is that the number of errors, that is all of these 24 were current stations, and here it's 17, so 13. So that our cyber search database actually had fewer errors than the government database. Now, this might be a bit disconcerting for the Department of Homeland Security. But what does this mean if we look at the cyber search results, which is a little bit more accurate? And an existing station configuration looking at a 1.5 mile buffer. And we're talking about the urban region of Los Angeles County south of Saugus, so we're not talking about Palmdale and so forth. Well, anyway, coverage at 1.5, 1.25 is relatively high. Now, we did a fishnet set of points. We did an optimal covering for the 1.5 miles, and excuse me here. What it amounts to is you see here that the current system uses 341 stations. You can do the same level of coverage in 254, which means that the total number of stations that are used in the county is about 34% higher than what would be the ideal configuration. Now, what we're trying to do is generate a system that we can automatically just point our tool at any county in the United States and start to determine the efficiency of fire service delivery, spatially at least. Now, even though that there are these differences, municipalities have different decision makers, the boundaries are contorted, I should say. For instance, one of the stations here operated by the county of of Los Angeles serves the city of Signal Hill, which is 2.2 square miles in size, completely surrounded by the city of Long Beach, that has their own fire department. And in fact, when you look at the coverage map, you'll find that the city, the county's fire department in the city of Signal Hill doesn't provide any extra coverage. It's already covered. So that we're starting to look at how these nuances of the boundaries are controlling the efficiency of these services. Now, I just want to leave you with the fact that if 30% of these stations are really necessary on the long run, that you're probably thinking about, well, it costs a lot of money to move a station. But it turns out that it's the manpower that is housed in the station, the equipment that's housed in the station, that costs the major amount of money. And in fact, in Goleta, we only have 5 or 6 stations. We've already moved 2 of them in the last couple years, and we're going to actually move another one sometime soon. In other words, it's not so expensive to move a station as compared to the issue of running them. So if you can reduce the total number of stations by 240, you might be able to reduce the crews by not maybe a like amount, maybe 20% rather than 30%. But if you're talking about 20% of $2 billion a year, you're talking about $400 million. So we do have a cyber search tool. There's not enough time to cover that, but the issue is that what we want to now look for is the patterns, not the anomalies like the donut holes, and why do those donut holes occur. But now what we want to do is look at the patterns of service across just the county of Los Angeles, but eventually virtually any county that we can point our cyber search tool on. Thank you. Thank you.
Thanks for this very interesting example. So my question would be about local effects on the small scale. So I've been working with the Montecito fire station because they are planning a 3rd fire station over there. And their problem doesn't seem to be the reachability in terms of the 1.5 miles or whatever, but that most of the houses in Montecito have gates. And it takes them around 30 seconds to open the gate if they have the key and so forth, but sometimes they have to speak to the people working there or something like that, or they don't have the keys. So how do you account for the fact that there may be a lot of variability in the particular needs, like, you know, streets with a lot of slopes or the gates problem and so forth?
Those are great anomalies. I don't think that Montecito is a good a good case example. I mean, it's really truly the exception, right? Where the movie stars and so forth that don't want to put up with Los Angeles live. There are some other kinds of anomalies that I'd like to raise here, and that is that not only is it, of course, the fire department, most fire departments consider the average time that it takes to respond, as well as the percentage of calls that are served within a certain time frame, as being indicative of whether they provided good service. And when I say they're talking about reaching the property where they've parked their vehicle and so forth, and so those issues about gates and so forth are usually not an issue with fire service. But there are some really kind of interesting issues associated with emergency response. For example, one of my graduate students and I have been able to garner about call records for ambulances in 4 different areas across the United States of approximately 1 million calls. Well, once we cleaned our data set, we had about 1 million calls. And one of the things that we could find out was the out-of-chute time. That is the time once the vehicle has been, or the crew has been told, hey, you need to you need to run off and make a call. The out of chute time, it was really quite an interesting variable because some crews did very well with out of chute times and other crews did not. And so there's that 15 seconds or even 2 or 3 minutes, for instance, that could make up that difference as well. So there are other components of the service call of which, to me, are more important than the gate. I think the homeowner has to worry about the gate, but that's my own opinion.
Rick, I have a question for you back here in the back. With emergency services on a network, how do you justify using a buffer that's a circle around each point? First point. Second point is, during the day, firefighters are rarely at their station. They're out at the store, they're performing maintenance on fire hydrants. How can you account for dynamic interactions of where the equipment is located versus an XY coordinate of where the fire station is located?
Well, that's a great question. You're talking about the actual dynamics of the service on a day-to-day basis, but within the context of planning, it's really important to recognize that historically, fire departments have drawn maps with circles. Okay, so I'm using the circle because that's the way they have typically thought about the problem. And even though that we easily have these capabilities, if we know what the travel times are, average travel times on a street, we can easily determine what those coverage radiuses are. But it turns out that we need to even know more than that because these are emergency vehicles that are making a response. And it turns out that it's a bit of a difficult issue to determine exactly how far a vehicle can get within a certain period of time, and throughout the day and so forth. And so the simple way of looking at it is a circle on a map. Now, in major metropolitan areas and so forth, this is probably not a bad approximation. But if you're talking about a rural area, maybe it isn't, except for the fact is that most of the people are living close to the roadway. And so the coverage of those areas that are not part of the road system and so forth. So there are some places that consider whether you've actually covered the roads or not as compared to just covering area. But when you're talking about a dense urban area, it's an approximation. I agree that it could be better, but this is the classic methodology that people and counties and fire departments use.